So the IMS includes 11 hydrophone systems, and these are designed to detect sounds traveling in the ocean sound channel. Now, this sound might be generated by earthquakes or underwater explosions, but the key point is it propagates very efficiently in water. Sound carries very well through water. And this means that signals can propagate tens of thousands of kilometers and still remain detectable. And this is what allows a small number of stations to cover a large volume of the Earth's oceans. Fundamentally, the hydrophone systems measure two things: the arrival time of the sound and the direction from which the signal comes, which we quantify by the azimuth. And our hydrophone stations are very high-quality systems. They measure very high-quality data, and this allows us to have some high precision. We have timing accuracy to around 1 second and azimuthal accuracy to within 1 degree. And this means that we have some very interesting and very particular data from the Tohoku event. What we're seeing here, this is our station at Wake Island. Over here is the epicenter of the Tohoku event. This station is 3,000 kilometers away. It takes about 30 minutes for sound to travel through the ocean there. It's worth pointing out at this stage that that's still very much faster than the speed at which the tsunami travels, so this data is still useful in terms of early warning. But what we're seeing over here is the sound itself being recorded at that station. And up here we have the azimuth. And as the line traces across, you'll see a line over here being traced back from Wake Island towards Tohoku. And you see that the sound doesn't come in at a single constant angle. It starts to the north, sweeps south, and then sweeps back up again. And well, there are many physical effects going on here, but among them is the fact that the rupture center, the place where the Earth's crust is cracking, isn't constant throughout the event. It's moving. And in this case, we're seeing evidence from 3,000 kilometers away that it's moving from the north to the south, then reversing in direction and going back towards the north. Now, this means that the rupture mechanism is not a simple one-directional motion, and that observation was supported by independent investigations of the rupture mechanism. And an example of this was presented by Lingseng Meng of Caltech at S&T 2010, which was the Science and Technology Conference held here by CTBTO at the Hofburg in Vienna. Now, this is a slide which has already been shown in Spiro's presentation, but I put it up here to remind you that we have this association with tsunami warning. But if you think back to the picture that I showed you of Wake Island, that station was very much in the path of the tsunami from the Tohoku event. So there were concerns that the station itself might be damaged by the tsunami. Fortunately, that wasn't the case, and the station survived. And to illustrate that, what we have here is data from a tide gauge at Wake Island. And in this period here, which is the several days before the event, you see the normal rise and fall of the sea level at Wake Island due to the normal tides in the Pacific Ocean. This is where the tsunami hits, and fortunately for us, the amplitude of the tsunami at Wake Island was only about 0.5 meter, so the station survived intact. Interesting to note that after the tsunami, the signal doesn't settle down back to its previous conditions for many days afterwards. So the Pacific was affected by this tsunami for many days after the main event. Now, because the station survived the tsunami, we also saw data from the passage of the tsunami as it went over the hydrophones. A hydrophone is a device for measuring pressure, and it will measure the pressure due to sound signals in the water, but it will also measure the pressure due to an increase in water depth above that sensor. So as the tsunami goes over, the water depth increases, then falls with the shape of the tsunami. And that pressure change is observed on the hydrophones. We have to filter the data down to very low frequencies, but we can see it. And that's what we have over here. This is a time-based. Notice that this is 4 hours, 2 hours, 0 hours, so a very long time-based signal. And on this axis here, we have frequency. And I've expressed it in terms of period. This is the time taken for a single cycle of the pressure. And the periods are of the order of 100 seconds, 500 seconds. These are extremely low-frequency signals, certainly nothing that we could hear as human beings. But what we see here, this red feature here, this is the passage of the tsunami over the hydrophones. And we have this diagonal stripe going from bottom left to top right. And the reason for that is associated with the hydrodynamics of tsunamis. The long waves, the low-frequency waves, travel the fastest and they arrive first. And that's what's happening down here. And then later on, the shorter waves, the higher frequency waves, come in later on. And so that's what the reason for this diagonal stripe and what appears to be some kind of echo beneath it as well. Now, this is just a pressure signal. And so what we can do is we can take it and we can shift it upwards many thousands of times in frequencies and turn it into another pressure signal that we as human beings can hear. If I click this, the first bang that you're hearing there is associated with the earthquake itself, and then that rather ghostly swept tone that comes through afterwards is the pressure signal caused by the passage of the tsunami over Wake Island. So in summary, the IMS hydrophone data recorded the sound generated by the Tohoku earthquake. It was forwarded already to tsunami warning centres. That's our present operation. And we observed the passage of the tsunami over the sensors near the Wake Island. And this is a unique data set, as the Executive Secretary mentioned in his talk. And we feel that there's unexploited potential in this data that could be used in the future for a more advanced or slightly improved tsunami warning. Thank you.